Hey folks, welcome to my very beige dining room. So real quick, we're talking about a new unit. In this unit, we're gonna be rolling stuff. We're gonna be rotating instead of sliding. So we've got to talk about rotational motion instead of translational motion, which we've been talking about. So what I've done is, and I know my wife's loved this, we built this small ramp here in the dining room, and then I've taken some Play-Doh from my kids and I filled these cat food cans up with it. Now what I did was I made a big ball, cut it in half, and then I've got about 45 grams in this one and 45 grams in this one. Don't come and rifle through my garbage to get the correct mass of these cat food cans. Anyways, what we're gonna do is we're gonna race them. So this one, all the Play-Doh is on the outside edge. This one, the Play-Doh is in the center. We're gonna see like, oh, hey, does it make a difference? Probably, hope so, because I've spent a ton of time cramming it into cat food cans. So we'll set these up to roll. Now, if we were just having these slide down the ramp, there's not going to be any dependence on mass. Like we've talked about that a bunch of times. They would start, beauty, they would start with the same PE. Wonderful. They would start with the same PE and they would end with the same kinetic energy. We're just seeing, is the same thing true now that we're rolling? Okay, so here's what happened. The ring kind of went off this way, right? But in the first couple seconds, the one where all the mass was in the center, that one really accelerated a lot faster. So we used to talk about inertia, and inertia is, just to remind us, it's a resistance to a change in motion. But really what we want to do now is we want to say it's translational motion. It's motion sideways and up and down, but not spinny motion. For spinny motion, we want to talk about the moment of inertia. So the moment of inertia is going to be resistance to changes in rotational motion. The formula for it. So with regular inertia, it's just equal to the mass. For the moment of inertia, it depends on a bunch of different stuff. The mass and the radius squared times, well, not times, and then summation of this. So basically, if we have a solid shape, we would break that solid shape up into an infinite number of minuscule pieces and then figure out how much each one massed and its radius from the center of rotation. That sounds like a job for calculus. We're not going to be calculating moments of inertia. It's not part of the AP curriculum per se, but we've got to know about moment of inertia. Now, on the AP exam years past, they did not give you this formula or give you a bunch of table of what these end up being. But basically, every different shape is going to have its different I value. So for instance, a hollow sphere and a sphere that's just got a thin shell are going to have two different I values, even if M and R are constant. So the whole point behind the cat food cans is one can had all the mass here, the other can had all the mass on the outside. Well, the one with the mass further from the center had a higher moment of inertia. It took longer for it to start rotating, and it kind of quit the race early, but had it not, it would have still lagged behind the other one. So the cat food can with the mass at the center accelerated down the ramp a lot faster. Now, page 223 in Giancoli has a short list. If I were preparing like I'm going to take the AP exam online for the first time, war room, I would find the ones in Giancoli. It's a short list, it's only like, 7 or 8. I would have those written down and somewhere accessible, or I would tab that part of Giancoli. Honestly, there's a lot more out there. Like Giancoli doesn't do hollow spheres, I would put hollow spheres in there as well. Just as many, well, not as many as I can find. If you have 1,000, that's gonna be too many. But, anyways, there we go. That's moment of inertia.